Great. Thank you very much for tuning in to this presentation, which is going to be introducing the new Model Uncertainty Intercomparison project, which we hope to kickstart with our meeting coming up on the 22nd of September. So my name is Hannah Christensen. I'm an Associate Professor at the University of Oxford, and I'm going to be leading us through this project. The goals of this presentation are firstly to give you a little bit of background about the project, but mostly I'm going to be talking about the proposed experimental design, the proposed protocol for the project, so that you arrive at the meeting with a good understanding of what we're suggesting we do. And then towards the end of this presentation, I'm going to be highlighting ways in which you can get involved and also highlighting some points of discussion for the meeting, so particularly decisions that we need to make and where we decide what our priorities are for the project. So let's get started then, firstly with a bit of background. So this project is really a joint initiative of the PDF and WGNI working group, so the Predictability, Dynamics and Ensemble Forecasting working group and the working group on numerical experimentation. And it comes about because of this primary overlapping interest between these two working groups, which is identifying model error. So here we're thinking both about systematic and random model error, but a particular focus of this project is going to be on random error. So this is the error that you might want to represent in an ensemble forecasting setting through a stochastic parameterization scheme. So at the joint WGNI-PDF meeting in Tokyo a couple of years ago, it was suggested that we organise a coordinated activity where we could study model error across a number of forecast models. And this project then is the result of that suggestion. So some key questions. So here I'm just brainstorming really, and I'm sure there are many more, and I'm very interested to hear your thoughts on the 22nd. But maybe the most fundamental question is, how should we best represent model uncertainty in our forecast model? So how can we best capture the effects of random error on our forecasts? Second question is, to what extent should this representation be model specific? I mean, do we believe that that somehow this is a fundamental property of all atmospheric models, or in fact do we believe that our the different structural decisions that have been made when making our models means that we're going to have to actually come up with quite different model uncertainty representations for different models? So this is a question we could address. A couple of other questions. I mean, can we design scale-aware schemes which don't need to be retuned as we change the resolution of our model? What about systematic model errors? That's something that we're interested in looking into in the context of this project. And then, I suppose, finally, what data or measurements do we have available that we can use to address these questions? And I'm sure there are many more questions that we can discuss in our meeting. And so I'm now going to move on then to talking a bit about the protocol that we've proposed for this project. So the very high-level description of the protocol is that we're going to take a high-resolution simulation and treat this as the truth. So this will be our benchmark, which we would like a low-resolution forecast model to be able to mimic. We're then going to go through a coarse graining procedure to measure the error in our low-resolution forecast model compared to this high-resolution benchmark. So top left, we start off then with some high-resolution data set, and we coarse grain this data set to the resolution of our forecast model in question. So that's the red box here. What we do is then we allow the high-resolution forecast model to evolve forward in time, and then we need to step forward our low-resolution field in some way using a forecast model. Then at our later time, again, we coarse grain the high-resolution data set, and we compare these two kind of coarse fields at this later time. That's 0.3 here. So the question then is, what can we use as our forecast model? And what we're suggesting is that we can use a single column model as the forecast model to step forward that low resolution field. So essentially we're going to use the coarse-grained high-resolution simulation to prescribe the initial conditions for a single column model, to provide the forcing required to run a single column model. So that includes the advected tendencies in temperature, horizontal winds and humidity. But also many single column models also require geostrophic wind and a vertical velocity. So we prescribe all these things from the coarse-grained high-resolution simulation. And we also supply the single column model with the boundary conditions at the surface that it needs to run, so surface fluxes as well as any kind of skin temperature. And why might we want to use a single column model? Well, firstly, by deriving the forcing fields from this coarse-grained high-resolution data set, we're actually able to effectively kind of provide the correct dynamical tendencies to that column. So that's the dynamics as represented by the high resolution simulation. And so the single column model receives the correct dynamical tendencies, which allows us then to target the uncertainty in the parametrization schemes, because any error in the forecast made by the single column model is really coming from these physics parametrizations. In addition to that reason, there's a couple more practical reasons why we might want to use a single column model. So firstly, it's single column models are very portable, they're very cheap to run. So actually what I've done in the past is take the single column model to the computer where the high resolution data is stored and run the single column model there, because as we all know, these high resolution data sets are not particularly portable. Another practical point which is relevant for some models, so spectral models like the IFS, I mean, these spectral models can't be run over a limited domain. So if we wanted to run a low resolution version of the IFS to step forward that field, we would have to pad the model with some other data outside of this domain we're interested in. But with a single column model, it's very simple. We just tile many independent single column models to cover whatever our limited domain is. And so obviously there are a number of other existing approaches that have been proposed to identify model error. So I won't spend too long on this slide. But perhaps you've come across the initial tendency approach. So this is the idea of looking within the data assimilation cycle at the tendencies that the model is, or the way in which the model is pushed back towards the analysis, so the analysis increments. And so that this has various benefits. If we look in the first column in this table here, so one key benefit of this approach is that we can decompose the evolution of the model. This is within the data assimilation cycle, so over just a few hours. We can decompose that model evolution into individual processes, so we can see what schemes are active over that very short period of time. A downside is that because it's happening within the data assimilation cycle, in some way we're comparing the model with its native analysis, and so this could mask errors because the analysis is not really the truth. Another alternative is the transpose AMIP approach, in which climate models are run in a weather forecasting mode. So we provide common initial conditions and then run the climate model from these common initial conditions just for a short period of time. So a big benefit of that approach is you don't need any data assimilation capabilities, which obviously you do in order to use the initial tendency approach. But a downside is that because we're specifying the common initial conditions, there may be inconsistencies between those initial conditions and your climate model of choice, which can lead to drifts. So that's a bit of a downside. With this approach that we're proposing here, we have both of the benefits of the other two approaches. So we can still decompose our evolution into single processes, and we don't need any data assimilation capabilities. But we also have the downside of the transpose AMIP approach, which is that if you take initial conditions which are not from that model's analysis, then there can be inconsistencies which you can see as a systematic drift. And so to deal with this issue of spin up, what I suggest is that we run each single column model simulation for a bit longer than we actually originally might have had in mind, and then discard the first part. So for example, in work that I've already done using the OpenIFS, we see substantial drifts in that model over the first hour of the run. And incidentally, you see these drifts actually even when the model is initialized from its own analysis. So it's really the model, it seems to be the model's kind of convection scheme is getting going in some way. And you see these drifts over the first hour. So in previous work, I was interested in looking at the error statistics over an hour period. So what I did then is run the OpenIFS for 2 hours and just consider the second hour. And so you can see then that I had these overlapping single column model simulations or forecasts that had been initialized from the high resolution. And then I just considered the tendency, the change in the single column model over the second hour and compared it to the change in the high res run. And this approach gives us a huge amount of information. So, I mean, what we end up with is the total change in the temperature, humidity, and horizontal winds in the high resolution data set, coarse grained to the low resolution grid, over, for example, a 1 hour time interval, as a function of all model levels, and then spatial location and forecast start time. And we have exactly the same thing from the single column model, so from our forecast model, but also decomposed into a dynamics and an individual parameterized tendencies. So we can see exactly which parameterization schemes are active where, and then by, for example, conditioning the error on what parameterization schemes are active, you can start to unpick what the source of that error might be. And so, I mean, for more details on the analysis that I've done already, I'd like to point you to this paper in the Quarterly Journal that came out earlier this year. And this is really a case study where I took a limited area high resolution simulation produced using the UK Met Office model and coarse grained it down to 30 kilometre resolution, and then was using the OpenIFS single column model as my forecast model to step it forward. But this paper then shows you some examples of the kind of analysis that you can do with this data. Before we move on to some of the decisions, some of the things I'd like us to talk about in the meeting, I'd like to say a couple more words about exactly how the coarse graining takes place, because this kind of highlights some of the decisions that we might want to take during the meeting. So firstly, how do I do the coarse graining? Well, I'm proposing that we will use a local area averaging as our coarse graining. So here I'm using this index I to indicate the fine scale box, and the index N is indicating the coarse scale box. So we start off with our fine resolution grid, and then imagine we want to coarse grain down to this lower resolution grid. In our local area averaging, we simply see we average all of the fine resolution I boxes that fall within our nth box, and weight them according to the fraction of that box that falls within the nth box. So this WNI is telling us the fraction of fine box I that occurs within large scale box N. Okay, second thing I'd like to talk about is issues to do with temporal interpolation. And so these issues come about because if we would like to use an existing high-resolution simulation instead of producing our own, we have to accept that these simulations are not archived at every time step of that high-resolution simulation. So, for example, the UK Met Office limited area run, which I used before, had a time step of 30 seconds, but was archived once an hour. And so the question then is, well, is once an hour a fine enough temporal resolution for our needs? So then we can only really assess the aggregated model error in the low resolution forecast model over that 1 hour time period. So what I've done in the past is then is to provide the forcing data for the single column model at intermediate time steps within that hour. I've linearly interpolated between the endpoints. So thirdly then, vertical interpolation. So this is actually quite a complicated and difficult problem. And it only occurs over regions where we have some terrain in our model. Essentially the question is, do we want to do our spatial averaging in the horizontal first before reinterpolating in the vertical, or do we do it the other way around? And to make this a bit clearer, I'm showing here some of our fine grid boxes. And so I've got a bit of kind of a horizontal line to indicate the pixelation of this, this mountain in our model. And the first thing that I do is I calculate the coarse resolution surface pressure. And so fairly uncontroversially then, that's the average of the high resolution surface pressure. And you can use then this coarse resolution surface pressure to define the model levels in your coarse resolution grid box. But the question then is whether we should first interpolate our fine resolution data onto those coarse resolution model levels, because they'll be different because of the different surface pressures. So do we first do the vertical interpolation and then average, or otherwise do we coarse grain along model levels in the fine resolution dataset and then do the vertical interpolation? I'm suggesting we do the latter. And that's because if we do the former and first do the vertical interpolation, we'll find that for grid boxes which are further up the mountain than the centre of the coarse resolution grid box, your vertical interpolation is going to have to extrapolate below the ground. And for grid boxes which are lower down the mountain than the middle of our grid box, the vertical interpolation is not going to use any of the information right close to the ground. So it seems to make more sense to me to do the horizontal averaging first. So that also means that things like surface temperature are going to be consistent with the surface pressure. But nevertheless, this is quite a fundamental decision that you have to make over these regions with orography. And so because of this, I actually propose that to get rid of this problem, we only focus on ocean regions for this project. Okay, a few more details. So our high resolution models generally have a lower top than our global models, and so to deal with this, I'm simply suggesting that we pad the data using ECMWF analysis. A couple of details about how to derive the forcing tendencies for the single column model. To get these advective tendencies, what I do is I estimate them all from the coarse grained fields. So I first calculate the coarse grained horizontal velocities and the coarse grained fields for temperature and humidity, etc. And then I estimate what then u dot grad is using this on this coarse grained scale to then give us this low resolution advective tendencies. And then finally, boundary conditions. So for the dynamic fluxes, we can get these we should be able to get these from the high resolution data set. So find out what the sensible and latent heat fluxes were that we used in the high res data set, and then we just coarse grain them and supply them to the single column model. For the static boundary conditions, anything to do with the land surface, for example, you could take those from your operational model. So what I'm requesting is that all single column models that are used in this project are going to follow a new format, the DEFI format. And so this is a standardized single column model protocol that has been recently proposed by a group of French researchers. And so, I mean, all it really does is it standardizes the format of the input and output files needed to run a single column model. So it specifies and it kind of gives naming conventions, things like that. And so actually there was an interactive workshop a couple of months ago, and there were a lot of different single column model groups who attended that workshop, discussed the protocol, and then made steps towards implementing it in the single column models. So if your single column model is not using the DEFI protocol, then I don't want that to exclude you from this project. But I would encourage you to maybe look into to seeing if you could implement it. But do just speak to me if that's not possible. Okay, so this then brings me to looking to the kickoff meeting. So there's a few decisions that I'd like us to make. Firstly, what high resolution simulation or simulation shall we use? So previous feedback on the protocol indicated that nobody really had any appetite for running a new simulation. So that means we need to select an existing simulation to use. And obviously we need to make sure that that simulation will suit our needs. So my suggestion is that we use a simulation from Diamond, from the Diamond project. And I'm suggesting that we use the ICON simulation. So the ICON simulation has got hourly data dumps, whereas some of the other simulations are coarser than that. It has all the variables that we need, and was run at a fine enough resolution that the convection scheme was turned off for that simulation. But this is up for discussion, and it might be also that we would like to try two different simulations. Secondly, which domain to focus on? So I've indicated that I would recommend looking at primarily an ocean region. So here's a list of different regions which we might consider, which we've compiled, approximately in order of preference, but this is up for discussion, and again we might want to consider more than one domain. And then which coarse grained resolution would we like to focus on? So ICON is 2.5 kilometers, so what would we like to coarse grain this to? And then finally, how should we really prioritize our time and resources? So I've alluded to the fact that we might want to choose, more than one simulation, more than one domain, etc. And so obviously any of these things will take more time, and we only have a finite amount of time. So what would we like to prioritize? If we do more benchmarks, we can consider the extent to which we can really treat one of these high resolution simulations as truth. I mean, how much do the statistics change if we move to a different benchmark? More domains, we can see how much statistics change at different regions, different latitudes in particular would be interesting. And then more resolutions would be important if we're interested in thinking about the scale awareness of schemes. There's also an option if we are particularly interested in thinking about a perturbed parameter type approach, a stochastic perturbed parameter approach, then either we need to have some sophisticated emulator of our single column model, or it's going to be quite an expensive Monte Carlo type approach where you run the single column model many times for each pixel with slightly different parameter values to see which one matches the high resolution simulation the best. And so obviously that's something that could be done, but that would take a lot of resources. So here then's an approximate roadmap for how we can move forward. So the decision seems to have already been made that we're not going to produce new simulations, but this can be discussed. So we're going to select an existing simulation and kind of bypass stage 1. Stage 2 is then coarse graining. So this is something that I will take the lead on once we've selected what simulations we would like to do. Stage 3 is then running the single column model simulations, and stage 4 is analysis. And so really I'd like to encourage or invite you to get involved into any or all of these stages. Scientific input into experimental design is of course very key, and so I hope we're going to start doing that at this meeting. Coarse graining, I've said I'll be leading on, but if other people would like to get involved here, then that would be very welcome. Single column model simulations is a really key part, so I'm glad to have representatives from lots of different modelling groups. I'm hoping that we're going to have some volunteers here to run each centre's single column models over these coarse grained data sets. And finally, analysis. I think obviously we're all looking forward to seeing what results we get out, but this is also then an area where I'd welcome contributions. So with that, I'll put up these references. I'd encourage you to look at the James paper if you want to see more information about exactly how I did the coarse graining and some of the tests I did to verify that this was a sensible approach. And the second paper in QJ I'd recommend you look at if you're interested in looking at how you can use this approach to constrain or motivate stochastic parameterizations. And then with that, I look forward to speaking to you all more on the 22nd. Thank you very much for listening.